Now let's consider linear dependent stack-ups. We will discover that these scenarios are as equally common as independent situations. The manner for determining the standard deviation will be different. Sometimes tolerance loops consist of dimensions that are dependent. In the picture shown here, dimension x and dimension y are dependent because they are associated with the same part. Effectively, x and y are correlated. This means that our determination of the standard deviation will be impacted based on this correlation. The average of the tolerance stack-up remains the same as before. However, the variances when adding and subtracting dimensions are changed based on a covariance factor, where covariance is the product of the correlation of the respective standard deviations of each dimension. Recognize that root sum square will adjust accordingly as well. In the equation shown here, R is the correlation between the dependent dimensions. Recall that correlation ranges from -1 to 1. A correlation near 0 means there is no relationship. Let's go back to the data in example 1. Part A and Part B are now dependent and have a correlation of 0.83. Note that the standard deviation of the stacked parts is 0.01535. Before, it was 0.01166. Now we can find the sigma tolerance limits to be 4.309 plus or minus 0.0944. Conservatively speaking, it is wise to consider dimensions associated with the same part to be dependent. Only if it can be conclusively shown that they are not can we assume independence. Some key indicators would be correlations close to 1 in magnitude, very few parts in the tolerance stack, or dimensions known to be significant contributors to variations of the system.